Have you ever found yourself gazing at the stars, perhaps lying on your back under the night sky, wondering about the secrets they hold? Their gentle twinkling seems so far away, yet they shine so brightly, carrying with them the light of history. As we look up at them, we often wonder, how did they come to be, and how do they eventually fade away? Today, as we embark on a peaceful journey through the life cycle of a star, I want you to relax, breathe deeply, and let go of any stresses or worries from the day. This video is not just an exploration of the cosmos. It's an opportunity for you to drift into a tranquil state, a moment to soothe your mind and calm your thoughts. As we explore the birth, life, and eventual death of a star, I invite you to allow yourself to simply relax, listen, and let your mind wander into a space of peace and comfort. Stars, like everything in the universe, go through an incredible journey of transformation. They are born from the dust and gas of space, growing through intense heat and pressure, until they begin the process of nuclear fusion. This fusion is what makes a star shine brightly for millions to billions of years, providing warmth and light. But like all things, stars do not live forever. Eventually, their core runs out of fuel, and they begin to expand, becoming red giants, before either exploding in a brilliant supernova or fading into white dwarfs. The story of a star's life is one of cycles, of creation and destruction, of light and dark. And just like these cosmic cycles, we too experience moments of change in our lives. As we embark on this calming journey through the stages of a star's life, remember that this video is more than just an educational exploration. It is meant to help you unwind, reduce the weight of your day, and guide you gently to sleep. If you have been feeling the weight of the world on your shoulders or struggling with feelings of sadness, know that you are not alone. Just as stars go through their cycles, so too do we. Even when it seems like the light of hope has dimmed, remember that just as stars are born, they die, only to give birth to new elements that create new stars and new life. The cycles of the stars remind us that there is always change, and change brings growth, renewal, and peace. In the next few moments, you will hear how stars are born in the cosmic nebulae, how they shine as main sequence stars, and how they eventually reach their end, either peacefully as white dwarfs or in a violent burst as supernovae. As we go through these stages, I want you to let go of any tension or anxiety you may be feeling. This story, though scientific, is filled with beauty and wonder, and it will take you on a journey through space that is meant to relax and soothe. Let the soft rhythm of the narration bring you a sense of calm, as though you are drifting among the stars themselves. With each word, allow yourself to sink deeper into relaxation, knowing that the universe is vast, and in its vastness, everything is connected. In the same way that stars go through their own life cycles, we too are a part of the cycle of life and growth. Sometimes life's struggles may feel overwhelming, but just as stars are reborn through supernovae or fade into the peace of a white dwarf, we too have moments of transformation and renewal. Let this video remind you that there is beauty in change, and that no matter how dark things may seem, new light always follows. Just like the stars, you have the ability to rise again, to shine once more, and to find peace. So, as we explore the incredible life cycle of stars, allow yourself to be transported into a place of stillness and restfulness. Let the rhythm of the star's journey guide you to a state of peace, and let the calming sounds of this story help you drift off to a restful sleep. As you listen to the peaceful unfolding of the star's journey, let the worries of the day melt away. This video was crafted not just to teach you about the universe, but to soothe your mind, calm your thoughts, and help you find rest. Each word, each explanation about the birth and death of stars is designed to ease you into a calm, sleepy state. Allow the soothing tone of the narration to guide you as the stars' lives unfold before you, slowly, peacefully, and with a sense of wonder. Just as the stars begin their cycle in the quiet of space, so too can you begin your cycle of rest and relaxation. So now, as we explore the fascinating life cycle of stars, let the knowledge of their beauty and their transformation bring you peace. Relax, breathe deeply, and imagine yourself floating amongst the stars, where all is calm, all is quiet, and all is connected. As the stars continue their journey, so do you, in a peaceful and calming rhythm that will help you gently fall asleep and wake up refreshed with a renewed sense of peace and hope. In the vastness of space, we are all part of something much larger, and just as stars transform, we too can transform, heal, and find comfort in the cycles of life. Let yourself drift away, knowing that you are part of something magnificent, just as the stars are. Stellar Nursery, the birth of a star. In the vastness of space, where the darkness seems endless, new stars are born in the most serene yet powerful way. These stars do not form out of nothing, but from the remnants of old stars, gas, and dust, floating freely through space. The process begins in regions of space known as nebulae, vast, dense clouds of gas and dust that are the birthplaces of stars. These nebulae are not quiet or still. They are dynamic, filled with swirling gases and particles that move in a slow, graceful dance. Within these nebulae, gravity begins its work. It pulls the gas and dust together, slowly compressing it into denser regions, known as protostars. As these clouds of gas and dust are drawn together by gravity, the material starts to heat up. The temperature rises steadily, and as it increases, nuclear fusion begins to stir within these infant stars. This is the spark that starts the star's life, a process that will continue for millions to billions of years. In the early stages, the protostar is not yet the shining beacon of light we recognize as a star. Instead, it's a dark, hot, dense ball of gas, still gathering the materials it needs to fuel its internal fusion reactions. During this time, the star is constantly growing, absorbing gas and dust. As the core temperature rises further, the heat and pressure become so intense that, eventually, nuclear reactions begin to take place. Hydrogen atoms are fused together to form helium, and in this process, an enormous amount of energy is released. This energy is the birth of light, and from this light, a star is born. But the journey is not yet complete. The protostar is only the beginning of a long process that will continue for billions of years, shaping the star into the powerful celestial body it will become. The energy released from nuclear fusion causes the star to shine brightly, and at the same time creates an outward pressure that counteracts the force of gravity pulling inward. This balance between the two forces, outward pressure from fusion and inward pull from gravity, allows the star to stabilize, entering the most important phase of its life cycle, the main sequence phase. During this phase, the star burns steadily, fusing hydrogen into helium, maintaining a perfect balance that keeps it shining brightly for millions to billions of years. But the process of stellar birth doesn't happen overnight. It's a slow, gradual process that can take millions of years. This gives us a glimpse into the sheer patience of the cosmos. The universe moves at a pace that is much slower than the human eye can perceive. And in this quiet patience, stars begin their incredible journey. As the protostar continues to collapse, eventually, the central core becomes hot enough to trigger the process of nuclear fusion, marking the official birth of the star. This stage is often referred to as the main sequence, the longest period in a star's life. During this time, the star is in a constant state of equilibrium. The balance between the inward force of gravity pulling everything toward the core and the outward push of energy from the fusion process keeps the star stable. Stars, like our sun, spend about 90% of their life in this stage, shining brightly in the sky and providing energy to planets like Earth. The nuclear reactions occurring at the heart of the star convert hydrogen into helium, releasing vast amounts of energy, which is what we see as the star's light. The creation of light from the fusion process is what allows stars to shine. It is through these fusion reactions that stars are able to provide the warmth and light that make life possible on planets like ours. But even during this stable period, a star's birth is not an instant event. It's a gradual process that takes time, millions of years in fact. From the moment the protostar begins to gather the dust and gas that will become its fuel to the moment it begins to shine brightly, it's a journey of slow and steady growth. This process is not always peaceful. It is filled with intense forces that create storms of gas and dust that can influence everything around them. The energy generated by nuclear fusion sends out waves of light, heat, and radiation, lighting up the surrounding nebulae. Over time, these bursts of energy begin to clear the surrounding gas and dust, and the newly born star begins to emerge from the nebula, now visible as a bright light against the backdrop of space. Throughout this process, the star's birth is marked by constant change and motion. The gas and dust surrounding the star are drawn toward it, creating a swirling disk of material known as the accretion disk. This disk is made up of gas and dust that have not yet been absorbed by the star, but instead are orbiting around it, slowly falling inward. This process is similar to the way the planets in our own solar system formed, slowly gathering material and adding to their mass. As the accretion disk orbits, it creates a glowing ring of light, and as the material falls inward, it heats up, releasing energy. The star's growth is also driven by the release of this energy, which helps the star continue to shine and maintain its balance of gravity and pressure. And so, the birth of a star is a process of both creation and destruction. Matter is drawn together, compressed, heated, and ignited to form light. As the star continues to shine, it casts away the remaining gas and dust surrounding it, leaving behind a glowing, steady light that will continue for millions of years. This light is the result of the energy produced by the star's ongoing fusion reactions. And this energy, in turn, creates a warm, glowing atmosphere around the star, which could, in time, support the development of planets and life. The birth of a star is not just the creation of light. It is the beginning of a cycle that can support entire ecosystems, provide energy, and sustain the growth of new stars and planets. In a sense, the birth of a star is the beginning of everything, the beginning of life, energy, and the universe itself. Nuclear fusion, the spark of life. In the quiet vastness of space, a star's birth is a slow and steady process. But what truly gives it life is the incredible phenomenon of nuclear fusion. Deep in the core of a young star, the temperatures and pressures become so intense that they trigger a powerful reaction. Hydrogen atoms, the simplest and most abundant elements in the universe, begin to collide and fuse together. As these atoms come together, they form helium, releasing an immense amount of energy in the process. This energy is what powers the star and allows it to shine brightly in the dark expanse of space. Nuclear fusion is the very spark of life for a star, and it's this process that fuels it for millions to billions of years. With each reaction, the star's core becomes a furnace of energy, and the light we see from distant stars is the result of these incredible reactions taking place deep within their centers. The process begins when gravity pulls together the hydrogen gas inside the protostar, causing the core to collapse under the immense weight of the surrounding material. As the core contracts, it becomes increasingly hot and dense, pushing the hydrogen atoms closer together. At a temperature of around 10 million degrees Celsius, the hydrogen atoms are forced into close enough proximity to overcome the electrostatic forces that naturally cause them to repel each other. This is the moment when nuclear fusion begins. Hydrogen atoms collide with such force that they fuse into helium, releasing an enormous amount of energy in the form of light and heat. This release of energy creates an outward pressure that balances the inward pull of gravity, stabilizing the star and allowing it to shine brightly for millions of years. The process of nuclear fusion is so powerful that it sustains the star, providing the energy necessary for it to remain stable, glowing, and alive. As fusion continues, it creates not just energy, but the building blocks for more complex elements. With every fusion reaction, heavier elements are formed from the simpler hydrogen and helium atoms, creating elements like carbon, oxygen, and even iron as the star ages. The fusion process begins with hydrogen turning into helium, but as the star evolves, it can fuse heavier elements in its core. This is how stars become the cosmic factories that create the elements we see throughout the universe. The carbon, oxygen, and iron produced in the core of stars are eventually released into space when a star dies, enriching the surrounding gas clouds and providing the materials for new stars, planets, and life itself. The beauty of nuclear fusion is that it's not just the creation of energy, it's the creation of the very building blocks that make up the universe around us. But the process of nuclear fusion is not without its challenges for the star. The balance between gravity, which pulls everything inward, and the outward pressure created by fusion is delicate. As long as these forces remain in balance, the star will continue to burn brightly, maintaining a stable size and temperature. However, when the star exhausts its hydrogen fuel, the core no longer has the energy to maintain this balance. The core will begin to contract once again, and the outer layers will expand, marking the end of the star's time as a stable main sequence star. This leads to the next stage in the star's life cycle, where it becomes a red giant, burning heavier elements like helium and carbon. But while the star may transition to a red giant and eventually reach the end of its life, nuclear fusion has already shaped the very structure of the universe. Through fusion, stars produce the elements that form everything around us, and without this process, the universe would be a very different place. The energy produced by nuclear fusion is not only what allows stars to shine, it's also what allows them to interact with the universe in a significant way. As stars burn their fuel, they release vast amounts of energy into space, heating up their surrounding environments and even causing the formation of planets, comets, and asteroids. This release of energy, in the form of light and radiation, travels across vast distances, allowing us to see the stars and feel their warmth from millions of light years away. This energy also influences the space around the star, shaping the way that matter behaves in the star's vicinity. The power of fusion extends beyond just the star itself. It has a ripple effect across the cosmos, influencing the formation of galaxies, solar systems, and even life. Without nuclear fusion, the universe would lack the energy necessary to create the complex structures we see today. When we think of nuclear fusion, we tend to focus on the massive stars, the ones that burn bright and hot. But fusion occurs at every stage of a star's life. Even when a star begins to die, fusion continues in its outer layers, producing new elements and releasing energy in the form of light and heat. As a star exhausts its fuel, it transitions through different stages of fusion, from hydrogen to helium, then to heavier elements like carbon, neon, and oxygen. This process continues in larger stars, until the core becomes so dense that it can no longer sustain the fusion of heavier elements like iron. At this point, the star faces its inevitable collapse, but even in its final moments, fusion continues to shape the fate of the star and the materials that surround it. The death of a star is not the end. It's merely the next chapter in a never-ending cycle of creation and destruction, all made possible by the very force of nuclear fusion. Nuclear fusion is the heartbeat of a star's existence. It is the force that powers stars, gives them life, and allows them to shine brightly for millions of years. Fusion not only provides the energy that sustains stars, but it also creates the elements that make up everything in the universe, from the air we breathe to the earth beneath our feet. As stars evolve and burn through their fuel, they release the products of fusion into space, enriching the cosmos and contributing to the ongoing cycle of stellar life and death. The power of nuclear fusion is an incredible force that shapes the universe in profound ways, and without it, stars would never be born, and life as we know it would not exist. As we continue to explore the universe and the stars that light our way, we must always remember that the spark of life, the energy that fuels the stars, comes from the process of nuclear fusion. It is this process, this incredible force, that drives the birth and death of stars, creating the cosmic cycles that shape the very fabric of our universe. The main sequence, the longest stage. The main sequence is the longest and most stable phase in a star's life. It is during this period that stars like our sun shine the brightest and burn the most steadily. Stars spend the majority of their lives in this phase, where they fuse hydrogen into helium at their cores, a process that produces the vast energy we see radiating outward as light and heat. The balance between the inward pull of gravity and the outward pressure from fusion keeps the star stable during this time, allowing it to maintain its size and brightness for millions, even billions, of years. During this phase, the star remains in a state of dynamic equilibrium, where the forces acting on it are perfectly balanced, resulting in the constant, steady glow we associate with stars in the night sky. The main sequence is the heart of a star's life, where it thrives, shines, and sustains the energy needed to create light. As the star enters the main sequence, it begins to burn hydrogen in its core, the simplest and most abundant element in the universe. This hydrogen undergoes nuclear fusion, where its atoms collide and fuse to form helium. In this process, an immense amount of energy is released in the form of light and heat, which radiates outward from the core and causes the star to shine brightly. The fusion of hydrogen to helium creates an outward pressure that counters the inward pull of gravity, keeping the star stable. This equilibrium between the two forces is what allows the star to maintain its size and brightness for such an extended period of time. For stars like the Sun, the main sequence phase can last for billions of years, during which they continue to burn hydrogen at a steady pace, providing light and energy to planets orbiting them. It is a time of stability, a moment in a star's life where everything is perfectly balanced. During the main sequence phase, the star's energy output remains relatively constant, but the core of the star is slowly converting hydrogen into helium over time. As the hydrogen in the core is used up, the core contracts slightly, causing the temperature and pressure to increase. This slight change causes the outer layers of the star to expand, but the star remains in its main sequence for a long time. It is this slow and steady burning of hydrogen that gives stars their brilliant, consistent light, allowing them to remain stable and predictable for vast periods. The energy from fusion flows outward through the star, and eventually, it is released into space as the bright light and heat we associate with stars. It is this light that sustains life on planets orbiting stars like our Sun, providing the warmth and energy necessary for life to flourish. The main sequence is the period in which stars are the most active, the most radiant, and the most influential in the universe. But even as stars shine brightly during the main sequence phase, their journey is not endless. The process of nuclear fusion, while incredibly stable, is not infinite. As stars continue to burn through their hydrogen fuel, the core gradually becomes richer in helium, and the amount of available hydrogen to fuse decreases. As the hydrogen supply runs low, the star enters the final stages of the main sequence phase. While the fusion process slows down, the star remains in this stage for the majority of its life, continuing to burn hydrogen at a steady rate until it exhausts the majority of its fuel. For most stars, this marks the beginning of the end of the main sequence phase, but it will take billions of years before the star's fuel supply is completely exhausted. Even as the hydrogen burns away, the energy released keeps the star glowing, and it continues to support life on planets around it. The main sequence is a long, peaceful period in the star's life, a time when it radiates its energy, supporting life on nearby planets and fulfilling its role in the cosmic cycle. As the star uses up its hydrogen, it begins to transition into the next stage of its life, the red giant phase. This marks the point where fusion moves beyond hydrogen and begins to focus on helium, creating heavier elements like carbon and oxygen. As the core contracts and heats up, the outer layers expand, and the star becomes hundreds of times larger than it was during the main sequence phase. But even as the star begins to transition, the main sequence phase remains an important part of its journey. During this time, the star is at its brightest and most stable, with energy radiating from its surface, fueling the growth of planets and continuing the cycle of stellar life. Stars in the main sequence phase serve as beacons in the universe, providing energy to planets, stars, and even galaxies, ensuring the ongoing cycle of birth and death throughout the cosmos. The main sequence phase is truly the longest and most defining period in a star's life. For stars like our Sun, this phase can last for about 10 billion years, with the star burning steadily and providing a stable source of light and energy to everything around it. During this time, stars maintain their size and shape, emitting steady light and heat, which is essential for the development of life on planets. But even as the main sequence phase provides the foundation for life, the star is slowly using up its fuel, and when that fuel runs out, it will undergo a dramatic transformation. The life of a star is cyclical, and while the main sequence phase is the longest, it is also just one chapter in the star's long and eventual journey. The next stage, the red giant phase, will bring new changes and a new phase of creation and destruction, leading the star toward its eventual end. But for now, the main sequence remains the most important and stable stage in the star's life, the time when it shines its brightest, provides the energy needed for life, and serves as the foundation for all that comes next. The main sequence phase of a star's life is an awe-inspiring period of stability, light, and energy. This stage defines the majority of a star's existence, allowing it to burn steadily and provide the warmth and energy necessary for life to exist on nearby planets. For billions of years, stars burn hydrogen in their cores, maintaining a perfect balance between the forces of gravity and the energy produced from fusion. This period of balance and light is the heart of a star's life, and it is only when this fuel runs low that the star begins to transform, expanding into a red giant and eventually ending its cycle. The main sequence is the longest stage of the star's life, the most stable and illuminating, and it plays an essential role in the creation of everything around us. As we look at the stars above us, remember that their bright light is the result of nuclear fusion, and their continued burning is the heartbeat of the universe itself. Stars, through their steady glow and energy, shape the universe, giving life to the planets and illuminating the night sky for generations to come. This keynote on the main sequence phase is written in a slow, soothing style that explains the stability and brilliance of stars during this key phase of their life cycle. The use of soft, ASMR-inspired tones helps maintain a relaxing and calming atmosphere while exploring the fascinating processes that occur within stars. Red giant phase, the expanding star. As a star ages and its core begins to deplete its hydrogen supply, it enters one of the most fascinating and visually striking stages of its life cycle, the red giant phase. This stage is marked by a dramatic transformation. What was once a steady, stable star begins to expand, becoming many times larger than its original size. The core of the star, which is no longer able to sustain the fusion of hydrogen, starts to contract under the immense pressure of gravity. At the same time, the outer layers of the star expand outward, cooling in the process, giving the star its characteristic red hue. It is during this period that stars like our Sun begin to shine with a new kind of brilliance, but also face the inevitable changes that signal the closing chapters of their life cycle. The red giant phase is both a time of beauty and power, and the precursor to the star's final moments. The transition into the red giant phase occurs gradually as the star begins to run out of hydrogen in its core. As the hydrogen fusion slows, the core contracts, causing the temperature and pressure within to rise significantly. This increase in pressure triggers the fusion of helium and other heavier elements in the core, creating more energy and further expanding the outer layers of the star. The result is a massive expansion, with the star swelling to hundreds or even thousands of times its original size. For stars like our Sun, this expansion will cause the outer layers to extend beyond the orbit of Mercury, Venus, and possibly even Earth. While the outer layers cool and the star takes on its red hue, the core becomes extremely hot and dense, fusing heavier elements like carbon and oxygen. This is a crucial stage in the life of a star. While it may seem like the end is near, this is just one of the most awe-inspiring moments in the cycle of a star's existence. As the star swells into a red giant, it begins to experience increased luminosity, meaning it shines much more brightly than before. This intense light, however, is not without consequences. The outer layers of the red giant are blown away by powerful stellar winds, which push the gas and dust into space, creating a glowing cloud known as a planetary nebula. These winds can strip the star of its outermost layers, and the result is a beautiful, swirling cloud of gas and dust that surrounds the star's core. These nebulae are some of the most stunning phenomena in the universe, often captured in spectacular images by astronomers. But while the outer layers are being cast off, the core of the red giant continues to contract and heat up, eventually preparing for the next stage of the star's life. The final moments before its death. The red giant phase is also the point in a star's life when it undergoes the most intense internal transformations. The fusion process that begins with hydrogen now shifts to heavier elements such as helium and carbon, which also undergo fusion in the star's core. This process allows the star to maintain its outward pressure, slowing the rate at which it contracts. However, the star is not immortal, and this stage marks the beginning of the inevitable end. The fusion of helium and other heavier elements will eventually stop, and the core will once again begin to collapse under its own weight. At the same time, the outer layers will continue to expand, cooling as they do, until the star is a massive, glowing, red ball of gas. It is during this phase that the fate of the star becomes sealed, whether it will go out with a violent supernova explosion or quietly fade into a white dwarf. The red giant phase is a period of tension, where the star is nearing the limits of its life, yet continues to burn brightly, creating an atmosphere of cosmic wonder. One of the most fascinating aspects of the red giant phase is its role in element creation. During this stage, stars are responsible for the formation of many of the elements that make up the universe, including elements like carbon, oxygen, and neon. As the core of the star continues to burn heavier elements, these elements are released into the surrounding nebula, enriching the interstellar medium with the building blocks for future stars and planets. The process of stellar nucleosynthesis in the red giant phase is responsible for the creation of essential elements that make life possible here on Earth. The carbon we breathe, The oxygen we rely on, and even the iron in our blood were all created inside stars like these, only to be scattered across the universe when the star dies. This is one of the most beautiful and poignant aspects of the red giant phase. The star's death is the beginning of the life of other stars and planets. The cycle of stellar life and death continues, shaping the universe with each passing moment. The red giant phase, though spectacular, is not without its dangers. As the star reaches the peak of its expansion, the inner layers of gas and dust become unstable, creating intense turbulence. This turbulence can cause the star to become unpredictable in its behavior, with some red giants exhibiting strange and erratic changes in their brightness and size. These fluctuations are the result of the complex processes occurring in the star's core, as it attempts to fuse heavier elements to maintain its size and brightness. While this chaotic period is short-lived, it's a reminder of the incredible forces at play inside stars as they near the end of their lives. The red giant phase is a time of intense pressure, both internally and externally, as the star prepares to face its final chapter. As the red giant eventually exhausts its fuel and can no longer support its own weight, it will collapse into its core and initiate the final transformation. For low to medium mass stars, this means shedding their outer layers to form a planetary nebula, leaving behind a dense white dwarf at their core. For high mass stars, this results in a catastrophic supernova, an explosion that scatters the star's outer layers into space and leaves behind a neutron star or black hole. The red giant phase, while it may seem like the star is nearing its death, is actually the moment that gives rise to the creation of new elements and new stars. As the star fades into its final form, it marks the end of its journey, but also the continuation of the cosmic cycle of birth and rebirth. The red giant phase is a time of immense change for a star. It is when the star expands, cools, and begins to burn heavier elements in its core. While it is nearing the end of its life, this phase is also the source of many of the elements that make up the universe. It is a beautiful and dramatic stage in a star's life, and it paves the way for the creation of new stars, planets, and even life itself. The red giant phase reminds us that the universe is in a constant state of change and transformation, and even the death of a star can lead to the creation of new life. Just as stars are born, they must eventually die, and in this cycle, they give rise to the building blocks of new worlds and new beginnings. This is the eternal beauty of the cosmos, and the red giant phase exemplifies the quiet power of stars as they reach the final stages of their life. Helium fusion, the creation of heavier elements. As stars enter the final stages of their life cycle, they undergo a remarkable transformation, the shift from burning hydrogen to helium fusion. This process is a pivotal moment in a star's journey, marking a transition from the stable, long-lasting main sequence phase to the more tumultuous and complex phases of their final days. As a star depletes its hydrogen supply, it begins to burn helium in its core, starting a new round of nuclear fusion reactions that are even more intense than before. The fusion of helium into heavier elements like carbon, oxygen, and neon not only alters the star's core, but also the entire structure of the star itself. These new fusion reactions generate an incredible amount of energy, causing the star to expand and shine with a new, more powerful light. It's during this phase that the star starts to lose its familiar characteristics and begins to look much different than it did during its main sequence phase. Helium fusion occurs in the core when the temperature and pressure are high enough to overcome the repulsive forces between the helium nuclei. As the star's core contracts under gravity, the temperature rises to about 100 million degrees Celsius, triggering the fusion of helium atoms into carbon. This new fusion process releases a tremendous amount of energy, causing the outer layers of the star to expand dramatically. The energy released from helium fusion causes the star to enter what is known as the red giant phase. As the core contracts and heats up, the outer layers cool and expand, turning the star a deep red hue. In this new expanded state, the star becomes unstable, and its outer layers begin to be shed through intense stellar winds. These winds push away the outer layers of gas and dust, creating a beautiful glowing shell around the star's core, often referred to as a planetary nebula. During helium fusion, stars begin to burn heavier elements in their cores, shifting from helium to even heavier elements like carbon, neon, and eventually oxygen. This process allows the star to maintain its energy output and slow the process of core collapse. As the star burns through heavier elements, it moves closer to its final days. The fusion of helium is crucial because it extends the life of the star, allowing it to shine longer and brighter. But this stage, like all others, is temporary. Stars will only continue to fuse helium for a relatively short period compared to their time spent burning hydrogen. Once the helium fuel runs out, the core once again becomes unstable, and the process of fusion will shift to even heavier elements like carbon and oxygen. The star is now in a state of rapid change, moving closer to its eventual end. It's at this point that the true power of stars is fully realized, their ability to create elements that will eventually form new stars, planets, and even life. Helium fusion in stars also leads to the formation of heavier elements, which are essential to the creation of everything we see around us. The elements created during this process, carbon, oxygen, and neon, are crucial for the formation of planets and life as we know it. It's these elements that will be scattered across space when the star reaches the end of its life, enriching the interstellar medium with the materials needed to form new stars, planets, and even life. This process of stellar nucleosynthesis is the cosmic factory that produces all the heavier elements in the universe. Without helium fusion, these elements would never have been created, and the universe would be a very different place. The creation of these elements during the later stages of a star's life is vital not only for the ongoing cycle of stellar evolution, but for the very existence of the world we live in. Each star is, in a way, a creator, bringing forth the building blocks that will one day form new worlds, new stars, and perhaps new life. As a star continues to fuse heavier elements in its core, it also experiences internal changes that make it more unstable. The creation of heavier elements increases the mass and density of the star's core, causing it to collapse under its own gravity. The heat generated by this collapse ignites the next round of fusion, which creates even more complex elements. The process is one of constant evolution. Just as hydrogen gave way to helium, helium gives way to carbon and oxygen, and so on, creating a chain of fusion reactions that will continue until the star reaches its final stages. With each new stage of fusion, the core becomes increasingly dense and hot, while the outer layers of the star expand and cool. The star's internal processes become more turbulent, and it begins to lose mass as it sheds its outer layers into space. The once stable, glowing sphere of a star begins to show signs of instability, and its fate is sealed as it moves toward its inevitable death. The fusion of helium and other heavier elements is the final attempt of a star to maintain balance before its core becomes so dense that it can no longer support the energy needed to counteract the pull of gravity. At this point, the star may enter its red giant phase, where the outer layers continue to expand, and the core contracts even further. This final phase of life sees the star going through a series of dramatic changes, each one bringing it closer to the end. Eventually, the star will lose its outer layers through stellar winds or a supernova explosion, leaving behind a dense core that can become either a white dwarf, neutron star, or black hole, depending on the star's mass. The creation of helium and the transition into heavier elements is part of a stellar life cycle that ensures the continuous evolution of the universe, creating the necessary ingredients for the birth of new stars and galaxies. In conclusion, helium fusion is one of the most important stages in a star's life. It's the moment when a star shifts from burning hydrogen to burning heavier elements, creating the materials that make up much of the universe around us. This process is not just a crucial part of a star's life cycle. It's a vital force that shapes the universe, creating the building blocks for everything we know and see. Through fusion, stars become cosmic factories, producing the elements that are essential for the creation of planets, stars, and life itself. Though helium fusion marks a temporary phase in a star's life, it plays a significant role in the cosmic cycle, ensuring that the universe remains a dynamic, ever-changing place. As stars continue to burn through heavier elements, they leave behind a legacy of creation and transformation that shapes the future of the cosmos. The stellar wind, the star's expanding outer layers. As a star approaches the final chapters of its life, its outer layers begin to take on a new form, driven by a fascinating and gentle force known as the stellar wind. This is a constant, slow stream of gas and particles that is expelled from the star's outer layers, pushed outward by the intense energy generated deep within its core. As the star enters its later stages, particularly during the red giant phase, the rate of this wind increases, and it becomes one of the most important forces shaping the star's transformation. Stellar winds are not destructive in the way we often think of cosmic events. They are a gradual, steady release of matter into the surrounding space, and they play a vital role in the life cycle of a star. These winds, while seemingly gentle, are a critical mechanism by which stars shed their outer layers, releasing them into the cosmos and enriching the interstellar medium with the building blocks for new stars and planets. The strength of the stellar wind increases as a star expands during its red giant phase. As the star burns heavier elements in its core, the outer layers, which are now much cooler, begin to be lifted by the energy produced in the core. These winds carry the star's outer material into space, where it spreads out and creates the planetary nebulae often associated with dying stars. The gas and dust expelled by the star combine with the surrounding space, forming intricate, colorful clouds that can stretch for light years. These nebulae are some of the most breathtaking phenomena in the universe, where the very essence of a star's life is scattered throughout space, providing the necessary material for future generations of stars. As the star sheds its outer layers, it sheds its past, and what remains is the dense core, which may eventually become a white dwarf, neutron star, or even collapse into a black hole. Stellar winds also serve an important role in regulating the star's internal processes. The outer layers of a star are not uniform. There are layers of gas that exist at different temperatures and densities. As the star's core undergoes fusion, it produces an immense amount of energy, but the outer layers can no longer hold all this heat and pressure. The stellar wind is one way the star releases this excess energy, preventing the buildup of too much pressure within the core. The process is gentle, almost imperceptible, but it is crucial to the overall balance of the star. As the wind pushes the outer layers away, the star's size changes, and its luminosity fluctuates, reflecting the gradual decline in its energy production. The loss of mass from the star through the stellar wind is a slow process, but it sets the stage for the eventual collapse of the star into its final form. While the stellar wind is a natural part of a star's evolution, it also has profound effects on the surrounding space. The gas and dust released by the wind become part of the interstellar medium, which is the material between stars in a galaxy. Over time, this material can be reabsorbed into new nebulae, giving birth to new stars and planets. The death of a star, through the expulsion of its outer layers, becomes the creation of something new, continuing the cycle of life and death that governs the cosmos. The material left behind by the stellar wind is rich in the elements necessary for life, including carbon, oxygen, and nitrogen. These elements are fundamental to the creation of planets that could support life, making the stellar wind a crucial ingredient for the future of the universe. As the star sheds its outer layers, it provides the building blocks for the formation of the next generation of stars, planets, and galaxies. In this way, the stellar wind is not just a process of decay, but a process of renewal and transformation. The energy released in the stellar wind is not just the result of fusion in the core. It is also a manifestation of the star's final attempts to stabilize itself as it moves toward its death. The outer layers, which are being heated by the fusion reactions below, begin to feel the pull of gravity less and less as the star becomes more and more unstable. The wind, which carries this outer material away, helps prevent the star from collapsing in on itself too quickly, allowing it to survive a little longer in its expanded form. This is a delicate balance, as the stellar wind must carry away enough material to reduce the star's mass, but not too much that it triggers the core's immediate collapse. As the star loses mass, the outer layers become less dense and more diffuse, causing the stellar wind to weaken as the star begins its final transformation. The planetary nebulae formed by the stellar wind are often seen as the final gift of a star's life, a peaceful and colorful display of gas and dust that represents the culmination of millions of years of evolution. These glowing clouds are not static. They are ever-changing as the gas and dust expand into space. As the star continues to shed its outer layers, the nebula grows larger, eventually dissipating into the surrounding space. The beauty of planetary nebulae is that they mark the end of a star's life while simultaneously giving birth to the next generation of stars. The gases expelled by the star carry the elements that will one day form new solar systems and potentially support life. It is a poignant and beautiful reminder that even in death, a star continues to influence the universe in profound ways. The process of stellar wind is a quiet, steady force that creates something new, even as it takes away the old. In conclusion, the stellar wind is an essential part of a star's final life cycle, marking the beginning of its transformation into something new. As a star sheds its outer layers through these winds, it enriches the surrounding space with the elements needed for future generations of stars, planets, and even life. The gentle expulsion of gas and dust not only signifies the star's decline, but also serves as a crucial step in the cosmic recycling process that sustains the universe's cycle of creation and destruction. Through the stellar wind, the death of a star gives rise to new life, and this constant transformation is the heartbeat of the cosmos. While the star may be dying, its legacy lives on in the elements it leaves behind, proving that even in death, stars continue to shape the future. Just as the wind carries the remnants of the star far away, it carries with it the promise of rebirth and the cycle of life that continues endlessly in the vastness of space. Supernova explosion for massive stars. As a massive star nears the end of its life, it undergoes a dramatic and explosive transformation. This event, known as a supernova, marks the final chapter in the life of a star much larger than our Sun. When a star runs out of fuel, the core becomes unstable, and gravity overpowers the outward pressure generated by fusion. As the core collapses under its immense gravitational force, it compresses into an incredibly dense object, releasing an enormous amount of energy. This energy causes a catastrophic explosion, ejecting the star's outer layers into space in a brilliant burst of light and radiation. The supernova is one of the most spectacular events in the universe, a moment of intense energy and beauty that signals both the end of the star's life and the beginning of a new cycle of creation. During the supernova explosion, the star's core becomes so dense that it can no longer support itself, leading to a catastrophic collapse. This collapse triggers the fusion of elements much heavier than those formed during the star's earlier stages of life, such as iron. The fusion of iron releases energy that is not enough to counteract the inward pull of gravity, causing the core to implode. This implosion compresses the core to such extreme densities that it causes the outer layers of the star to be expelled at nearly the speed of light. The explosion is so powerful that it can outshine an entire galaxy for a brief moment, illuminating the surrounding space with brilliant light. The force of the supernova is strong enough to trigger the formation of new stars and planets from the debris left behind. The remnants of the explosion scatter heavy elements like carbon, oxygen, and gold into the surrounding space, enriching the interstellar medium with the building blocks for new worlds. The supernova explosion is not only a breathtaking display of cosmic power, but it also plays a critical role in the cycle of life in the universe. When the massive star explodes, it releases enormous amounts of energy into space, creating shock waves that spread through the surrounding gas and dust. These shock waves are responsible for triggering the formation of new stars, as the energy from the explosion compresses nearby gas and dust, causing it to collapse into new stellar nurseries. The elements released during the supernova, such as carbon and oxygen, are the same elements that make up the planets and life as we know it. In this way, the death of a star leads to the creation of new stars and planets, continuing the cycle of birth and death in the cosmos. While a supernova is the violent death of a massive star, it also serves as a cosmic seed, planting the seeds for new life to emerge from the ashes of the old. When a star undergoes a supernova explosion, the core that remains behind can take two very different paths, depending on the mass of the star. If the remaining core is not massive enough to collapse into a black hole, it will become a neutron star, a dense, compact remnant that is only about 20 kilometers in diameter but contains more mass than our Sun. Neutron stars are incredibly dense, so much so that a single teaspoon of neutron star material would weigh as much as a mountain. These remnants of supernovae are sometimes observed as pulsars, rotating neutron stars that emit beams of radiation. The intense gravity near a neutron star is so powerful that it can bend light and space around it, creating a warped view of the surrounding universe. Neutron stars are fascinating objects, offering a glimpse into the extreme conditions that occur in the death throes of massive stars. Their existence is a reminder that even in the star's death, there is transformation, and something new emerges from the cataclysmic explosion. However, if the remaining core is massive enough, it will collapse even further, creating a black hole, a region of space where the gravitational pull is so intense that nothing, not even light, can escape. The creation of a black hole from a supernova is one of the most profound and mysterious processes in the universe. The intense gravity of a black hole warps space-time itself, creating a singularity, a point of infinite density at the core where the laws of physics break down. A black hole's event horizon, the boundary beyond which nothing can escape, marks the ultimate fate of the collapsing star. Anything that crosses this boundary is lost to the black hole, forever trapped in its gravitational pull. While the exact mechanics of black hole formation are still a subject of research, the moment of a supernova explosion is one of the most crucial in the life cycle of a massive star, leading to the birth of one of the most mysterious and fascinating objects in the universe. The explosion of a supernova also generates powerful gamma rays and X-rays, which can have a profound effect on the surrounding space. These rays can be so intense that they can alter the chemical composition of nearby planets and stars, influencing the evolution of future solar systems. A supernova's shock waves and radiation can also trigger the formation of new stars in nearby nebulae, perpetuating the cycle of life and death in the cosmos. The supernova explosion is, in a way, the ultimate recycling process, as the materials from one star's death become the raw material for the creation of new celestial bodies. The explosion also serves as a cosmic reminder of the sheer power and energy that exist in the universe, forces that are beyond our comprehension, but also essential to the growth and evolution of galaxies, stars, and even life itself. The supernova explosion is one of the most powerful and beautiful events in the universe. It marks the end of a massive star's life, but also serves as the beginning of a new chapter in the cosmic cycle. Through the explosive release of energy, a supernova scatters the elements created by the star into space, enriching the universe and giving birth to new stars, planets, and even life. The death of a star is not just an end, but also a beginning, a transformation that creates the materials necessary for new generations of stars and galaxies. Whether it ends as a neutron star or collapses into a black hole, the fate of a supernova is as dramatic as the life it lived, and it reminds us that in the cosmos, even the most violent events can lead to the birth of something new. Stars live, die, and give rise to new wonders, ensuring the ongoing cycle of creation and destruction that shapes the universe we know. Neutron star or black hole, the end of the line for massive stars. As a massive star reaches the end of its life, the fate of its core becomes one of the most mysterious and fascinating outcomes in the universe. After the violent explosion of a supernova, the remnants of the star's core face an uncertain future depending on its mass. If the core is not massive enough, it will become a neutron star, a dense, compact object that remains a powerful and enigmatic relic of the once glowing star. If the core is massive enough, however, it will collapse further, creating a black hole, one of the most intriguing and incomprehensible objects in space. Both neutron stars and black holes are the ultimate results of stellar death, marking the final moments of a star's journey, but also the beginning of something profoundly significant in the universe. Let's begin with the creation of a neutron star. After a supernova explosion, if the core left behind has between 1.4 and 3 times the mass of our Sun, it will collapse into an extremely dense and small object known as a neutron star. The gravitational force acting on the core causes the protons and electrons in the atoms to combine, creating neutrons, which are subatomic particles without an electrical charge. This process transforms the core into a compact object with a mass that is several times greater than the Sun, but only about the size of a small city, roughly 20 kilometers in diameter. The result is a star with incredible density, where just a spoonful of material from a neutron star would weigh several billion tons on Earth. The intense gravity of a neutron star is so powerful that it warps space-time itself, and this extreme gravity causes light to bend around it, creating a distorted, almost surreal view of the universe. The idea of a neutron star challenges our understanding of physics, as it pushes the limits of matter's density, making it one of the most fascinating and puzzling objects in the universe. The creation of a neutron star marks the end of the star's life, but it also brings new mysteries. One of the most striking features of neutron stars is their ability to spin at incredible speeds. Some neutron stars, known as pulsars, rotate several times per second, emitting beams of radiation from their magnetic poles. As the star spins, these beams sweep across the sky, resembling a cosmic lighthouse. And if Earth happens to be in the path of these beams, we see them as pulses of light. This pulsating effect is what gives neutron stars their name, and their regular rhythm is a constant reminder of the extreme forces at play in these objects. The intense magnetic fields surrounding a neutron star are also incredibly powerful, far greater than those produced by any magnetic object on Earth. These fields can distort nearby space, creating strange effects that scientists are still trying to fully understand. As strange and enigmatic as they are, neutron stars provide valuable insight into the nature of matter and gravity under extreme conditions. However, if the core of the star is more massive than the threshold needed for a neutron star, it will continue to collapse inward under its own gravity. The forces at play become so extreme that they result in the creation of one of the most mind-boggling objects in the universe, the black hole. A black hole forms when the star's core collapses to an infinitely small point, known as a singularity, where gravity is so strong that not even light can escape its pull. At this point, the laws of physics as we know them cease to operate in a conventional way. The space surrounding the singularity is called the event horizon, and it marks the boundary beyond which nothing, not even light, can escape. The immense gravity within a black hole warps space-time itself, creating a deep well in the fabric of the universe. Anything that crosses the event horizon is lost forever, pulled into the singularity, where the concept of time and space breaks down completely. It is this mysterious and incomprehensible nature of black holes that has fascinated scientists and captured the human imagination for centuries. Black holes, though invisible, can be detected through their interaction with nearby matter. When matter falls into a black hole, it accelerates and heats up, emitting high-energy radiation in the process. This radiation can be detected by telescopes, allowing astronomers to infer the presence of a black hole, even though it cannot be seen directly. Black holes also have a profound effect on their surroundings, influencing the motion of nearby stars and gas clouds. For example, the supermassive black hole at the center of our galaxy, Sagittarius A, exerts a tremendous gravitational pull on the stars in its vicinity, causing them to orbit at incredibly high speeds. This is just one example of how black holes can shape the structure of entire galaxies. While the creation of a black hole is the violent end of a star's life, it is also the beginning of a new cosmic cycle, influencing the formation of new stars and the structure of the universe itself. In addition to their fascinating properties, black holes also play a crucial role in galactic evolution. The process of accretion, where matter spirals into a black hole, can generate massive amounts of energy, forming active galactic nuclei, AGN, and quasars, some of the most luminous objects in the universe. As matter is drawn into the black hole, it forms a rotating disk of gas and dust, called an accretion disk, which can heat up to millions of degrees, emitting radiation across the electromagnetic spectrum. The intense gravitational forces near a black hole can also cause relativistic jets of particles to be ejected from the poles, further influencing the galaxy's structure and dynamics. In this way, black holes are not only the remnants of dead stars, they are active participants in the cosmic landscape, shaping the galaxies in which they reside. The death of a massive star, whether it leads to the formation of a neutron star or a black hole, is one of the most profound and fascinating events in the universe. These remnants, born from the collapse of a star's core, serve as both a culmination of a star's life and a powerful force that shapes the universe. Neutron stars offer a glimpse into the extreme limits of matter and gravity, while black holes challenge our understanding of space and time itself. Both are the products of a star's transformation, and both are critical to the ongoing cycle of creation and destruction that defines the cosmos. The death of a star, through the creation of either a neutron star or a black hole, is not an end, but rather a beginning, one that continues to shape the universe in ways we are only beginning to understand. These stellar remnants, through their incredible density, gravity, and energy, are the universe's ultimate testament to the power of transformation, illustrating that even in death, stars continue to influence the cosmos in ways we are only beginning to uncover. White dwarf, for smaller stars. As a star exhausts its nuclear fuel and passes through its red giant phase, it reaches a turning point in its life cycle. Unlike the massive stars that end their lives in a spectacular supernova explosion, stars with smaller masses, like our Sun, take a quieter path towards the end of their journey. These stars don't have the necessary mass to undergo a supernova. Instead, they shed their outer layers, leaving behind a dense, hot core known as a white dwarf. A white dwarf is the final remnant of a smaller star's life, a faint yet powerful object that quietly marks the end of a star's once illustrious shine. The formation of a white dwarf is a peaceful yet profound event, signifying the completion of the star's life cycle. The birth of a white dwarf begins when a star enters the red giant phase, having exhausted the hydrogen in its core. In this phase, the outer layers of the star expand significantly, shedding vast clouds of gas and dust into space, creating a glowing planetary nebula. These outer layers are ejected into the interstellar medium, leaving behind only the dense core, which is what we come to know as the white dwarf. The remaining core is primarily composed of carbon and oxygen, and although it is no longer undergoing fusion, it continues to emit light due to its residual heat. White dwarfs are incredibly dense objects, with masses similar to that of the Sun, but they are packed into a volume similar to the size of the Earth. This immense density means that white dwarfs are some of the densest objects in the universe, second only to neutron stars and black holes. Despite this density, their size remains relatively small, and they shine with a faint ethereal glow that slowly fades over time. The process leading to the creation of a white dwarf is one of stability and slow transformation. Unlike the explosive deaths of more massive stars, the death of a smaller star is a quieter, more gradual event. After the star sheds its outer layers, the core no longer has enough mass to support further fusion reactions, and as a result, it becomes a white dwarf. The outer layers of gas and dust disperse into the surrounding space, leaving the core to cool over time. Over the course of billions of years, the white dwarf will continue to cool and lose its brightness, eventually becoming a cold, dark object known as a black dwarf. However, this process takes such an immense amount of time that no black dwarfs are thought to exist yet, as the universe is not yet old enough for a white dwarf to fully cool into this state. Despite their small size, white dwarfs can be quite fascinating due to their remarkable density. A single cubic centimeter of a white dwarf would weigh about a ton on Earth, a striking contrast to its size. This incredible density is due to the star's mass being packed into a very small space. The pressure at the core of a white dwarf is so intense that it causes the electrons in the atoms to be squeezed together, preventing further collapse due to electron degeneracy pressure. This is a quantum mechanical effect that occurs when the electrons are packed so tightly that they resist being compressed any further, thus stabilizing the star and preventing it from collapsing completely. The balance between gravity and degeneracy pressure keeps the white dwarf stable, allowing it to exist for billions of years before it begins to cool. Even though white dwarfs are no longer capable of fusion, they still release residual heat, which gradually diminishes over time. This faint glow is the last vestige of the star's former brilliance, but it will eventually fade as the white dwarf continues to cool. While the white dwarf no longer produces energy through fusion, it is still a key player in the cosmic recycling process. The material ejected from the red giant phase and the white dwarf's eventual cooling contribute to the interstellar medium, enriching space with the elements needed for the formation of new stars, planets, and possibly life. It's through this cycle of death and rebirth that the universe continues to evolve, creating the building blocks for the next generation of cosmic wonders. The death of a star, in the form of a white dwarf, is not the end of its story, but the beginning of a new cycle of cosmic creation. As white dwarfs continue to cool, they fade into obscurity, becoming black dwarfs, cold, dark remnants of once glorious stars. However, this cooling process takes longer than the current age of the universe, meaning that no black dwarfs have yet formed. In essence, the journey of a white dwarf is one of gradual transformation, a long and slow fading into nothingness over billions of years. But even in their final moments, white dwarfs play a critical role in shaping the universe, contributing to the creation of new stars and galaxies through the elements they release. Their slow cooling serves as a reminder of the vast timescales on which the universe operates, where the end of one life leads to the potential for new beginnings. Though their light eventually fades, the legacy of white dwarfs lives on, continuing to influence the cosmos long after they have ceased to shine. White dwarfs represent the final, peaceful end of a star's life for those of smaller mass. These remnants, though faint and dim, carry with them the essence of the stars they once were, containing the elements that will go on to create new stars and planets. They are the epitome of quiet transformation, enduring for billions of years, slowly fading as they cool and become black dwarfs. The journey of a white dwarf is a slow and steady one, filled with immense density, cosmic importance, and a quiet beauty that can only be appreciated in the grand context of the universe. The creation of a white dwarf marks the end of a star's life, but it is also the beginning of its legacy, influencing the future of the cosmos in ways that continue to shape the stars and planets that follow. The cycle of birth, life, and death of stars is a beautiful, eternal process, and the white dwarf is a quiet, unassuming reminder of the cosmic forces at play in the universe. The end of a white dwarf, cooling into a black dwarf. After a star like our sun reaches the white dwarf phase, its life slowly begins to wind down, though it may seem like an unassuming, quiet end. These stellar remnants no longer undergo fusion, yet they continue to radiate the last remnants of heat from their previous energy-generating processes. As the white dwarf cools over billions of years, it begins to fade away, becoming darker and dimmer as time passes. Eventually, this slow process will lead the white dwarf into its final form, the black dwarf. A black dwarf is a theoretical object, one that hasn't yet been observed because the universe is still too young for any white dwarf to have fully cooled into one. However, the process itself is fascinating, as it represents the ultimate end of a star's life. The slow, inevitable cooling of the white dwarf serves as a reminder that stars, no matter how powerful they once were, all eventually come to an end. The process of a white dwarf cooling into a black dwarf is a gentle and gradual one, taking place over trillions of years, far longer than the current age of the universe. This extended timescale means that, for now, no black dwarfs exist, as no white dwarf has yet had enough time to cool completely. But this slow fading is inevitable for all white dwarfs, and it is part of the natural progression of stars. The cooling process occurs in stages, with the white dwarf radiating its remaining heat into space until it is no longer able to emit light. As it cools, the white dwarf dims and becomes increasingly cold, its once bright surface giving way to a dark, frozen core. Eventually, the white dwarf reaches a temperature so low that it no longer radiates energy in any form. At this point, the star becomes a black dwarf, invisible to the human eye, its glow completely extinguished. While the black dwarf itself is not a phenomenon we can observe directly, it still plays a crucial role in the cycle of stellar life and death. Even as it fades into nothingness, the material that once made up the star continues to affect its surroundings. The heavy elements produced by fusion in the white dwarf, such as carbon and oxygen, are scattered into space, enriching the interstellar medium with the building blocks of future stars and planets. These elements will be incorporated into new nebulae, where they will contribute to the formation of new stars, continuing the cycle of life in the universe. So, even as a white dwarf cools into a black dwarf, it continues to contribute to the cosmos, playing an essential role in the ongoing creation of stars and planets. The process of stellar death and rebirth is a constant, dynamic cycle, and the transformation of a white dwarf into a black dwarf represents the final chapter of one star's story, but also the beginning of the next. As the black dwarf settles into its quiet, cold state, it remains a faint, dark remnant of the once vibrant star it used to be. Its mass is no longer sufficient to trigger any further fusion, and it no longer contributes to the brightness of the universe. But the black dwarf is far from meaningless. It is an essential part of the cosmic balance. The cooling and fading of these stellar remnants is part of the larger story of the universe's evolution, and their existence is a testament to the patience and stillness that the cosmos requires. The energy from a black dwarf is so minimal that it cannot sustain life or contribute to any observable phenomena, making it a quiet, peaceful presence in the universe. However, it represents the final, inevitable end of the star's journey. Its quiet transition from brightness to darkness, from energy to stillness. This peaceful fading mirrors the passage of time itself, as stars and galaxies continue their eternal cycle of birth, life, and death. The quiet nature of a black dwarf is in stark contrast to the violent deaths of more massive stars, which end their lives in explosive supernovae or collapse into black holes. The death of a white dwarf is peaceful and serene, a slow cooling process that takes place over unimaginable timescales. In a way, this quiet end is fitting for stars like our Sun, which have spent billions of years shining steadily, providing light and warmth to the planets around them. The transition from a white dwarf to a black dwarf is a subtle, almost imperceptible process, but it's one that underscores the stillness of the universe as time moves forward. Over the course of trillions of years, the black dwarf will continue to exist in a state of perfect quiet, awaiting the moment when it will finally lose all its energy and become a frozen relic of the cosmos. The black dwarf, though invisible, represents the final, most peaceful end of a star's life. As it cools and fades, it becomes a part of the universe's distant future, a future where the bright, shining stars of today will eventually all turn to black dwarfs. The universe itself is constantly evolving, and the process of star death is a crucial part of that transformation. The cooling of white dwarfs into black dwarfs is just one of the many ways in which stars contribute to the ongoing cycle of cosmic change. Even in their final moments, white dwarfs, and eventually black dwarfs, continue to influence the interstellar medium, enriching it with elements that will go on to create new stars and planets. This slow process is a reminder that, in the universe, nothing ever truly disappears. Every star that dies leaves behind something essential for the creation of new life. whether in the form of elements or the cosmic dust that will one day become the building blocks of the next generation of stars. The transformation of a white dwarf into a black dwarf marks the quiet and final end of a star's life, but it also represents the ongoing cycle of cosmic evolution. This peaceful transition is part of the larger story of how stars, even in death, contribute to the ever-changing nature of the universe. The process takes trillions of years, and while we cannot yet observe black dwarfs, we know that they will play a role in shaping the distant future of the cosmos. The cooling and fading of these stellar remnants is a reminder of the vast timescales on which the universe operates, where the passage of time is so slow that the universe's ultimate fate remains unknown. As we look at the stars above us, we are reminded that they too, like all things in the universe, have a beginning and an end. Their legacy lives on in the elements they leave behind, continuing the cycle of creation that will go on for billions of years. The white dwarf's slow cooling into a black dwarf is a peaceful, quiet end to a star's story. Yet it is also a crucial part of the grand cycle that defines the universe, the role of supernovae in element creation. When a massive star reaches the end of its life, it goes through a breathtaking and violent event known as a supernova explosion. This explosion is one of the most powerful and energetic events in the universe, and it marks the death of the star. However, despite the destructive nature of a supernova, this explosive death plays a crucial role in the creation of many of the elements that make up everything around us. The energy and force unleashed during a supernova are so immense that they allow for the creation of elements heavier than iron, such as gold, uranium, and platinum, which are then scattered across the universe. These elements are essential for the formation of planets and life as we know it. And without supernova, the building blocks of life would never have existed. In this way, the death of a star is not just an end. It is a beginning, a transformation that continues the cosmic cycle of creation and destruction. During a supernova explosion, the core of the star collapses in on itself under the influence of gravity. This collapse causes the core to become incredibly dense, triggering a massive burst of energy that sends shock waves outward, tearing apart the star's outer layers. This release of energy causes the surrounding gas and dust to heat up to millions of degrees, allowing for the fusion of elements that normally wouldn't be possible. These extreme conditions create an environment where elements heavier than iron can form, and it is this process that produces many of the elements that make up the Earth, our Sun, and even our own bodies. As the star explodes, these newly created elements are hurled into the surrounding space, enriching the interstellar medium and providing the raw materials for new stars, planets, and potentially even life. The explosion of a supernova is, in essence, a cosmic recycling process, where old stars give way to new elements that will go on to form new worlds. In addition to creating heavy elements, supernovae also play a significant role in shaping the structure of galaxies. The energy released in a supernova explosion creates powerful shock waves that ripple through space, causing nearby gas clouds to collapse and form new stars. These shock waves help to create stellar nurseries, where new stars and planetary systems are born from the remnants of older stars. In this way, the death of one star gives rise to the birth of many more. Supernovae also influence the movement of galaxies themselves, as the energy from these explosions can push gas and dust throughout the galaxy, redistributing matter and triggering the formation of new stellar systems. The explosion of a single massive star can set off a chain reaction that changes the entire structure of its galaxy, demonstrating how interconnected the universe truly is. The role of supernovae in element creation cannot be overstated. Without these explosive deaths, the universe would lack many of the elements that are essential for the formation of planets and life. The elements created during a supernova explosion Carbon, oxygen, nitrogen, gold, and iron are the building blocks for everything from the dust that forms new stars to the materials that make up life on Earth. These elements are scattered across the universe, and over time, they mix with other gases and particles, eventually forming new stars and planets. The explosion of a supernova is the ultimate act of cosmic creation, as the death of a single star leads to the creation of the very elements that will eventually give rise to new worlds. This process is a beautiful example of how life and death in the universe are interwoven, with the end of one cycle giving rise to the next. As these newly created elements spread across the cosmos, they contribute to the formation of new solar systems, enriching the material from which new stars and planets are formed. The heavy elements that are created in the intense heat of a supernova are responsible for the creation of rocky planets, such as Earth, and the essential elements needed for life, such as carbon and oxygen. These elements were forged in the cores of massive stars, and when the star dies, they are dispersed throughout the galaxy, eventually becoming part of the material that forms new planets and stars. The material released by a supernova also contributes to the creation of dust clouds and nebulae, where new stars are born. The life cycle of stars, both the birth and the death, is not just a process of destruction, but a constant renewal of the materials that make up the universe. The energy released in a supernova explosion is so great that it can be detected from millions of light years away. This energy is released in the form of gamma rays, X-rays, and visible light, all of which provide astronomers with valuable insights into the nature of stars and the universe itself. Observing a supernova is one of the most awe-inspiring experiences for scientists, as it allows them to study the extremes of physics in real time. The light emitted from a supernova can be brighter than the entire galaxy it resides in, making these events some of the most luminous and powerful phenomena in the universe. Even though a supernova lasts for only a few weeks to a few months, its impact on the surrounding space can last for millions of years. These cosmic fireworks mark the death of one star, but they also provide the energy and materials needed for the formation of future stars, galaxies, and planets. Supernovae are not just the dramatic deaths of massive stars. They are the engines of creation in the universe. Through these explosive events, stars scatter the heavy elements necessary for the formation of new stars, planets, and even life. A supernova is a cosmic catalyst, driving the cycle of birth, death, and rebirth in the universe, ensuring that new stars and worlds continue to emerge from the ashes of old ones. The death of a star in a supernova explosion is a reminder that, in the universe, even in destruction, there is creation. The process of stellar death and rebirth continues, with each supernova marking the end of one story and the beginning of another. In this way, supernovae are not just the death throes of a star, but the heralds of the future, bringing with them the building blocks for the next generation of stars, planets, and life. The cycle continues, the birth of new stars, the death of a star, particularly through events like supernovae, or the shedding of outer layers in red giants, marks the end of one chapter in the cosmic book of life, but it simultaneously sows the seeds for the birth of new stars and celestial bodies. The very elements created in the core of stars during their long lives and scattered into the cosmos at their death become the building blocks for the formation of new stars, planets, and even life itself. The death of a star is not an end, but a transition, one that feeds into a never-ending cycle of creation, destruction, and rebirth. As the remnants of a star's death spread through the interstellar medium, they enrich the surrounding space, providing the raw materials needed for new generations of stars to form. This constant cycle of death and rebirth is what drives the evolution of galaxies, solar systems, and everything within them. After a supernova explosion or the formation of a white dwarf, the elements released into space, carbon, oxygen, neon, and many other essential materials, remain in the surrounding interstellar medium, where they begin to mix with other gases and particles. Over time, the material from these dying stars forms dense clouds of gas and dust, called nebulae, which become the birthplaces of new stars. These nebulae are the cosmic nurseries where new stars are born from the remnants of older ones, continuing the cycle of creation. The dense regions of these nebulae collapse under the force of gravity, and as the material gathers together, it begins to heat up and form a protostar. This protostar is the earliest stage of a new star, and as it continues to gather mass and heat, it eventually ignites the process of nuclear fusion, giving birth to a new shining star. The formation of new stars from nebulae is a slow and intricate process, but it's essential to the evolution of the universe. The star-forming regions, known as stellar nurseries, are filled with hydrogen, the primary fuel for stars, and other heavy elements created in previous generations of stars. Over millions of years, these clouds of gas and dust are compressed by gravity, triggering the formation of protostars and eventually leading to the birth of fully fledged stars. This process is not without its challenges, as the collapse of gas clouds can be slow and requires the presence of powerful forces to overcome the internal pressure of the gas. The newly formed stars begin to shine with the energy produced by nuclear fusion, illuminating their surrounding nebulae and pushing away the leftover gas and dust, clearing the way for the formation of planetary systems. Once the star is born, it enters the main sequence phase, where it spends most of its life, continuing the cycle of fusion and producing light and heat. These stars, like our Sun, will go on to provide energy for the development of planets, potentially supporting life in the future. The materials that were once part of the previous generation of stars are now part of the new solar system, enriching it with the elements needed to form planets and even life. The process of star formation is not only a cosmic event, it's a foundational process for the creation of the universe as we know it, as it gives rise to the galaxies, planets, and everything that exists within them. New stars are born out of the death of older stars, and this cycle continues across the vast reaches of the universe, driving the ongoing transformation of galaxies and solar systems. As new stars are born from the remnants of older ones, they bring with them the potential for new planets to form as well. The material released during a star's death, especially in the case of planetary nebulae, contains the elements necessary for the creation of rocky planets, elements like silicon, iron, and magnesium. These elements combine with gases in the nebula, gradually forming the solid cores of new planets. As the new stars begin their own cycles of fusion, the material surrounding them starts to condense and form planets, moons, asteroids, and comets. In this way, the death of a star contributes to the birth of not only new stars, but also the formation of new solar systems, some of which may one day support life. This ongoing cycle of creation, driven by the death of stars and the birth of new ones, ensures the constant renewal and evolution of the cosmos. Even though stars eventually die, they leave behind the most crucial ingredients for the formation of life. The elements created and scattered during their deaths are the foundation of life itself, from the carbon in our bodies to the oxygen we breathe. The energy released during a supernova explosion or through stellar winds during the red giant phase also plays a role in shaping the structure of galaxies and the creation of new stars. In fact, without the deaths of stars, the universe would lack the raw materials necessary for life to exist on planets like Earth. The death of one star becomes the seed for new stars and planets, continuing the cycle of creation in the universe. The process of stellar death and rebirth is not just a force of destruction, it is also a force of creation, making it an essential part of the cosmic cycle. The death of a star is not an end, but the beginning of something new. The materials left behind by dying stars, whether through a supernova explosion or the shedding of outer layers, become the building blocks for the creation of new stars and planets. The cycle of life and death in the cosmos is ongoing, with each new generation of stars born from the remnants of the previous one. The process of star formation from nebulae is the ultimate reminder that the universe is in constant flux, constantly evolving and transforming. Even though stars eventually fade and die, their legacy lives on in the elements they produce, ensuring the future of the universe is always changing, always creating. This eternal cycle of creation and destruction is what drives the evolution of galaxies, stars, and planets, continuing the dance of life in the vastness of space. And so, as one star fades, another is born, perpetuating the cycle that fuels the creation of the universe. This endless cycle is what gives the cosmos its beauty and mystery, always creating, always transforming, never standing still.